Hello everyone, here's Mustafa. This is our second lesson in Unit 7 Equilibrium. We'll speak in this video about dynamic equilibrium. Let's get started. In the previous lesson, I differentiated between reversible and irreversible reactions. In this lesson, we'll speak about equilibrium reactions, which are all reversible reactions. So the first condition for a reaction to be at equilibrium, it has to be reversible reaction. Let's speak about one of the examples of an equilibrium reaction. We have here, if we have nitrogen gas plus hydrogen gas, it should make ammonia. This is Haber process, but ammonia will not be formed directly. When nitrogen and the hydrogen will react, we will have in the beginning of the reaction, initially we have no products, but after hydrogen and nitrogen will react, we will start observing that ammonia is formed. Of course, we should have it balanced. So we should have here ammonia is formed, and the rate of formation of ammonia in the beginning is high. For that reason, I'm drawing this big arrow like that, because in the beginning the rate is high because we have high concentration of reactants. But after a while, the reaction, well, we can say that the dynamic equilibrium has established. Then we will have here all the species are available at the same time. Here we have dynamic equilibrium where we have all the reactants and the products available at the same time, and we have the rate of the forward equal to the rate of the backward reaction. We have to observe something which is very important. We have here, this is gas, ammonia is gas. Of course, we have here nitrogen and the hydrogen and ammonia. All of them are gases. For that reason, we should have a closed system. Why? Because if one of the species which are making the reaction escaped, we will no longer have the equilibrium reaction. So we should have a closed system. We should have the rate of the forward reaction equal to the rate of the backward reaction. We should have fixed amount of the reactants and the products. In the next slide, we'll speak about the characteristics of the equilibrium state. Now, what are the characteristics of the equilibrium state? First of all, at equilibrium, we have the rate of the forward reaction is equal to the rate of the reversible reaction. For that reason, we draw the arrow like that, the reversible arrow like that, with two identical and opposite arrows. We have here the forward rate and the reverse rate. They are equal. Okay, so if we don't have equal arrows like that, it means that it's not dynamic equilibrium. Or if we have the arrow like that, this is not dynamic equilibrium. We should have the reversible arrow displayed like that. Otherwise, we don't have dynamic equilibrium. The condition number 2, or the property number 2 for the equilibrium state, macroscopic properties are constant. What does it mean by that? We have the concentration of the reactant and the concentration of products are constant. As you can see here in this graph, the equilibrium, there is no change in the amounts. Products will not increase or decrease. Reactants will not increase or decrease, but we will have a fixed amount of reactants and products. Okay, they are not equal. Take care, they are not equal. They might be equal, but it's not a condition for the concentration of reactants and the products to be equal. But what is the condition? They have to be fixed or constant, which means that they are not increasing or decreasing. The condition number 3, equilibrium can be attained only in a closed system. Why we should have a closed system? If we are speaking about the decomposition of calcium carbonate is giving calcium oxide and the carbon dioxide. Carbon dioxide can react again with calcium oxide to form calcium carbonate. But what will happen if we don't have a closed system? Carbon dioxide might escape. If carbon dioxide escaped from the system, we will not be able to form calcium carbonate again. For that reason, we should have a closed system to allow the reaction to move to the opposite direction. Number 4, all species in the chemical equation are present in the equilibrium reaction mix. If we have here this reaction for the Haber process for the formation of ammonia from nitrogen and hydrogen, we should have all three species in the system at equilibrium. We should have nitrogen, hydrogen, and ammonia at the same time. If we are lacking one of them, if one of them escaped, we do not have equilibrium at this moment. Number 5, equilibrium can be attained from either direction. We have here a reversible reaction, so it could be from reactants to products or from products to reactants.